Welcome to part 2 of a 3-part series on storage and delivery of medical gas, based on Egan's Chapter 41 for RES 180. We'll go over how to calculate the duration of gas flow remaining in a gas and a liquid oxygen cylinder. We'll describe how to store, transport, and use compressed gas cylinders properly. You should, when you're done with this, be able to distinguish between gas supply systems, describe what to do if a bulk oxygen supply system fails, and differentiate among safety systems that apply to various equipment connections. We're going to start our discussion today with talking about gas cylinders. Medical gases are stored either in portable or high-pressure cylinders or in large bulk reservoir systems. Bulk reservoir systems require a separate distribution system to deliver gas to a patient, and we'll talk about those later in this second part of a 3-part series. With gas cylinders, these are the containers that are used to store and ship compressed or liquid medical gases. They're high pressure. The design, manufacture, transport, and use of these cylinders are very carefully controlled by both industrial standards and federal regulations. Gas cylinders are made of seamless steel and are classified by the U.S. Department of Transportation, or DOT. D-O-T. They are classified according to their fabrication method. A DOT type 3A cylinder is made from carbon steel. A DOT type 3AA container is manufactured from a steel alloy that's tempered for higher strength. Markings and identification. Medical gas cylinders are marked with metal stamping on the shoulders, and this supplies specific information. Although the exact location and order of the markings vary, the respiratory therapist should be able to identify several key pieces of information. The letters DOT or ICC, Interstate Commerce Commission, are followed by the cylinder classification, either 3AA or 3A, and the normal filling pressure in pounds per square inch. Below this information usually is the letter size of the cylinder, E, G, H, etc., followed by the cylinder serial number. A third line provides the mark of ownership, which is often followed by a manufacturer's stamp or mark, and a mark identifying the inspecting authority. An abbreviation indicating the method of the cylinder manufacturer is usually on the opposite side of the cylinder. Also in this area is information about the original safety test and dates of all subsequent tests. Safety tests are conducted every 5 to 10 years as specified by Department of Transportation regulations. During these tests, cylinders are pressurized to 5/3 of their service pressure. While the cylinder is under pressure, technicians measure the cylinder leakage, expansion, and wall stress. The notation EE followed by a number indicates the elastic expansion of the cylinder in cubic centimeters under test conditions. An asterisk next to the test date indicates DOT approval for 10-year testing. A plus sign means the cylinder is approved. For filling to 10% greater than its service pressure. An approved cylinder with a service pressure of 2015 psi can be filled to 2200 psi. After hydrostatic testing, cylinders are subjected to internal inspection and cleaning. Cylinder safety relief valves. In a closed cylinder, any increase in gas temperature increases gas pressure. Should the temperature increase too much, as in a fire, the high gas pressure could rupture and explode. To prevent this type of accident, all cylinders have high-pressure release valves of some type. These release valves are often of three basic types: frangible disc, fusible plug, and spring-loaded. The frangible metal disc ruptures at a specific pressure. The fusible plug melts at a specific temperature. The spring-loaded valve opens and vents gas at a high set pressure. In each case, the activated valve vents gas from the cylinder and prevents the pressure from becoming too high. Most small cylinders, like E cylinders and below, have a fusible plug relief valve. Most large cylinders have a spring-loaded relief valve. These safety relief valves are always located in the cylinder valve stems. A shows a post and yoke stem, valve stem for E and AA for small valves. B shows the threaded valve outlet of a large H cylinder. How a cylinder is filled depends on whether its contents will be gaseous or liquid. Some gases stored in liquid form can remain at room temperature, but others have to be maintained in a cryptogenic or super low temperature state. Let's talk about compressed gases first. A gas cylinder normally is filled to its service pressure, the pressure stamped on the shoulder at 21.1 degrees centigrade or about 70 degrees Fahrenheit. However, approved cylinders can be filled to 10% greater than the service pressure, or 2200 psig. Liquefied gases. Gases with critical temperatures greater than room temperature can be stored as liquids at room temperature. These gases include carbon dioxide and nitrous oxide. Rather than being filled to a filling pressure, cylinders of these gases are filled according to specific filling density. The filling density is the ratio between the weight of the liquid gas put into the cylinder and the weight of water the cylinder could contain if it were full. The filling density for CO2 is 68%. This system allows the manufacturer to fill a cylinder with liquid CO2 up to 68% of the weight of water that a full cylinder could hold. The filling density of nitrous oxide is 55%. Cylinder pressures for gases stored in the liquid phase, like carbon dioxide and nitrous oxide, are much lower than for gases stored in a gas phase. Because the liquid does not fill the entire volume of the cylinder, the space above the liquid surface contains a gas in equilibrium with the liquid. The pressure in a liquid-filled gas cylinder equals the pressure of the vapor at any given temperature. Pressure in a cylinder depends on its state of its contents. In a gas-filled cylinder, the pressure represents the force equal to compress the gas into its smaller volume. In contrast, the pressure in a liquid-filled cylinder is the vapor pressure needed to keep the gas liquefied at the current temperature. So how do we measure a cylinder's contents? Well, that depends on if it's gas as pictured in A or if it's liquid at room temperature like B. Because let's talk about compressed gas cylinders first, as pictured in A. For gas-filled cylinders, the volume of gas in a cylinder is directly proportional to its pressure at a constant temperature. What gas law does that sound like? If a cylinder is full at 2200 psig, it will be half full when the pressure decreases to 1100 psig. To know how much gas is contained in a compressed gas cylinder, one only needs to measure its pressure. Liquid gas cylinders, as pictured in B, are a little different. The pressure doesn't relate to the amount of liquid remaining. Only the weight of the cylinder indicates the amount of gas inside. In fact, the cylinder pressure gauge will read full in a liquid gas cylinder until it is absolutely empty. So you must go by weight. Estimating duration of cylinder gas flow. When a cylinder of therapeutic gas is used, it's often necessary to predict how long the contents will last at a given flow. The duration of flow of a cylinder can be estimated if the following are known: the gas flow, so how much is going to the patient, the size of the cylinder, is it an H tank or an E tank, and the cylinder pressure at the start of therapy. So do you have a full tank, 2200 psig, 1800 psig, or maybe it's only half full, 1100 psig. For a given flow, the more gas a cylinder holds, the longer it will last. So an H tank will last longer than an E cylinder at the same flow. The higher the gas flow, the shorter the cylinder emptying time. So if your patient is on 6 liters, you're going to drain that E cylinder quick. If they're on a half a liter, it's going to last longer. The duration of flow from a cylinder is directly proportional to the amount of gas in there and inversely proportional to the flow, as expressed in the following formula. Duration of flow is equal to contents divided by flow. The units commonly used in the United States for measuring these quantities are not the same. Cylinder contents are generally specified in cubic feet or gallons, whereas gas flow normally is measured in liters. Rather than memorizing various cylinder contents and constantly converting metric and English amounts, the user can quickly calculate duration of flow by using a cylinder factor. Some of the two most common cylinder factors that we use are 0.28 for an E tank and 3.14 for an H tank. When the factor for a given gas and cylinder is known, calculating the duration of the flow is simple by applying the following equation. Duration of flow in minutes is equal to pressure in psig times the tank factor divided by flow in liters per minute. Again, duration of flow in minutes, how many minutes will the tank last, is equal to the pressure in the tank in psig times the cylinder factor divided by flow being used by the patient in liters per minute. You always need to allow for a margin of safety in estimating cylinder duration of flow. So we always round down. A great rule of thumb to remember: A full oxygen cylinder running at 10 liters per minute lasts about 60 minutes, an hour. A full H cylinder lasts at least 10 times longer, or about 10 hours. These are two simple rules to estimate flow duration. For example, a half-flow E cylinder running at 10 liters per minute would last only 30 minutes, whereas a full H cylinder running at 5 liters per minute lasts more than 20 hours. Estimating duration of liquid cylinder gas flow. The only accurate method for determining the volume of gas in a liquid-filled cylinder is by weight. Because 1 liter of liquid oxygen weighs 2.5 pounds and produces 860 liters, yes folks, I said 860 liters of oxygen. In its gaseous state, the amount of gas in a liquid cylinder can be calculated with the following formula. Amount of gas in a cylinder is equal to liquid O2 weight times 860 divided by 2.5 pounds per liter. After the amount of oxygen remaining in the cylinder is determined, the duration of gas in minutes can be calculated with the following formula. Duration of gas in minutes is equal to the amount of the gas in the cylinder in liters divided by the flow in liters per minute. Let's talk a little about cylinder gas safety. How do we store these cylinders? The following guidelines apply to cylinder storage. Store gas cylinders in racks or chain cylinders to wall to prevent them from falling or becoming damaged. The following guidelines for cylinder safety are recommendations of the National Fire Protection Agency, NFPA, and the Compressed Gas Association, CGA. For ease of use, these safety guidelines are divided into cylinder storage, transportation, and use. Do not store combustible material anywhere near your cylinders. Store away from sources of heat and light. Store flammable gases separately from gases that support combustion. Keep a cylinder cap in place if the cylinder is not in use. Be sure to post no smoking signs near your storage units, and store liquid oxygen containers in a cool, well-ventilated area. Cylinder transportation and cylinder use. Use cylinder carts with a securing mechanism as pictured here. Keep protective cylinder caps, also pictured here, in place during transportation, and protect gas cylinders from striking other cylinders or objects to avoid damage to the safety devices, valve stems, and the cylinder itself. Avoid dropping, dragging, or rolling cylinders when in transport. Do not transport cylinders for use that are not appropriately labeled. Secure gas cylinders at a patient's bedside in a way that prevents them from falling. Secure cylinders to a wall with a chain, bind, or chain them to a suitable cart, or support the cylinder in a stand. Do not use flammable materials. Open the cylinder valve slightly to remove dust, dirt before attaching the regulator. When slightly opening the valve, ensure no one is standing in front of the valve and say, "I'm cracking the tank" before doing it, so the cylinder can be brought to the patient's bedside. Never use cylinder valves or regulators that need repair, and do not alter or deface cylinder markings or color. Never place cylinders near sources of heat. Never secure cylinders to movable objects unless the object has an apparatus that can contain the cylinder safely, like a tank cart. Ensure the connection between the regulator and the cylinder valve is an American Standard safety system for H and G cylinders and a pin index safety system for E cylinders. And when oxygen is in use, post a no smoking sign. Bulk oxygen. Pictured here is a bulk oxygen storage facility. Bulk oxygen is used to meet large oxygen needs of healthcare facilities. Systems often hold at least 20,000 cubic feet of gas. Oxygen may be stored in either gas or liquid form, but liquid storage is the most common. When needed, the oxygen flows from the central source throughout the facility through a piping system with outlets conveniently located throughout the hospital. A bulk O2 system has several advantages over portable cylinders. Although initially expensive to construct, bulk oxygen systems are far less expensive over the long term. Bulk O2 systems are less prone to interruption. These systems eliminate the inconvenience and hazard of transporting and storing numerous cylinders. Bulk O2 systems regulate delivery pressure centrally, eliminating the need for separate pressure-reducing valves at each outlet. These systems also operate at a low pressure, making them much safer than high-pressure cylinders. Safety standards for bulk oxygen systems are set by the NFPA, or National Fire Protection Agency, and are subject to further control by local fire and building codes. There are three types of centrally located gas supply systems. One is an alternating supply system or cylinder manifold system, a cylinder supply system with a reserve supply, and a bulk gas system with a reserve. We'll talk about the alternating supply or cylinder manifold system first. This consists of a large, normally H or K size cylinders, of compressed oxygen banked together in a series. This alternating supply system has two sides, a primary bank and an alternating reserve bank. When the pressure in the primary bank decreases to a set level, a control valve automatically switches over to the reserve bank. Pictured here is an alternating supply system with nitrous oxide, probably supplying an OR. Again, this is a gas cylinder manifold system. The alternating supply system is composed of primary and reserve banks which alternate to charge the piping system. Cylinder supply system with reserve supply. This consists of primary supply, secondary supply, and reserve supply. When the primary gas supply is depleted by demand, this supply system automatically switches to the secondary supply. The last type is the bulk gas system with a reserve. This is most commonly used in large health facilities for economic, safety, and convenience reasons. A small volume of liquid O2 provides a very large amount of gaseous oxygen and minimizes space requirements. Safety precautions. The National Fire Protection Agency sets standards for the design, construction, and placement and use of bulk oxygen supply systems. A key provision in these standards is a requirement of a reserve or backup gas supply to equal the average daily gas usage of the hospital or facility. To meet this requirement, most large facilities have a second smaller liquid stand tank. Smaller facilities may use a cylinder gas manifold as a backup. Failure of the bulk oxygen supply systems have been reported with very major problems. Failure of a bulk oxygen supply can be life-threatening to any patient receiving oxygen or gas-powered ventilatory support. For this reason, the respiratory care staff must be prepared. Adherence to an established protocol is a quick way to identify and prioritize all affected patients. When the affected patients are identified, staff members move to appropriate backup equipment to the bedside, like portable H cylinders, bag mask resuscitators. Trained personnel bypass the failed system and provide the needed patient support while engineers determine the cause of the failure and correct it. Distribution and regulation. The primary function of the distribution and regulation system is to deliver oxygen and medical air to the bedside at a usable pressure, in this case 50 psig. This is accomplished through the central piping system. The central piping system is used to deliver compressed gas to all areas throughout the hospital. Gas pressure is reduced to a standard working pressure of 50 psig at the bulk storage location. The main alarm warns of any pressure drops or interruptions in flow from the source. Zone valves are located conveniently throughout the system. Zone valves may be closed for system maintenance or in case of fire. Pictured here is a central piping system. You can see outside gas storage going in to the facility, the basement, first and second floors. Wall outlet, main panel alarms, and zone valves are all pictured. Here are zone valves for oxygen, medical air, and vacuum. These are seen in each fire safety area. Safety index connector systems. There are 3 systems that are used to ensure correct gas source. The American Standard Safety System, or ASSS, for large cylinders and their attachments. This prevents accidental misconnections. It was adopted in the United States and Canada. The ASSS provides standards for threaded high-pressure connections between large compressed gas cylinders, sizes F through HK, and their attachments. Specifications exist for more than 60 different gases and gas mixtures. Pictured here is a typical American Standard Supply System connection used to attach a reducing valve to a large high-pressure cylinder. The pin index safety system is used for small cylinders up to and including size E and their attachments. Cylinders have a yoke-type connection. The exact position of pins and pinholes may vary for each gas. The most common for respiratory care use are the 2-5 pinhole position for oxygen and the 1-5 pinhole position for air. The diameter index safety system is used for low-pressure gas connectors. It is found at the outlets of pressure-reducing valves, outlets of central piping systems, and inlets of blenders, flow meters, and ventilators. Oxygen and air diameter index safety system connections are pictured here. The two shoulders of the nipple allow the nipple to unite only with a body that has a corresponding boring. If a match is incorrect, the nut will not engage in the body threads. The difference in the shoulders and bore between oxygen and air disconnections is evident in A and B. B is much bigger than A. Pictured here is your pin index safety system for oxygen at the 2 and 5 position. Pin index safety system positions 1, 2, 3, 4, 5, and 6. Pin index safety system, diameter index safety system, and American Standard Safety System are all pictured here. Thank you. That concludes part 2 of storage and delivery of medical gases. You've been a great audience. Have a great day.